Howdy folks, this discussion is going to be all about data and image compression using the singular value decomposition. As per usual, at the GitHub link in the description, you'll find a Jupyter notebook with all the code used in this video, a bunch of extra written notes, and also a list of references. Before we get started, I also want to note that the first time that I saw this technique in a numerical linear algebra course years ago when I was a student, it absolutely blew my mind, and so hopefully those of you that might be seeing this for the first time, it also really shows you just how powerful and interesting linear algebra can be. So many of you probably already know this by now, but for those of you that don't, all images are effectively just matrices. Each pixel of the image corresponds to a value of the matrix, and in this case for our boat image, those values are integers, and those integers are between 0 and 255. Now depending on where that value falls on the scale, it will determine how light or how dark that pixel is going to be shaded, which makes up our entire image. And with all images basically just being matrices, we could do matrix-like operations on them. So here you can see this is a transpose of our boat image. But more importantly though, we can do matrix decompositions. However, before we do that, I want to take you over here to show you where this boat image comes from. This comes from University of Southern California's Signal and Image Processing Institute's image database, where you'll find a ton of very popular images that you'll find all throughout a whole wide variety of literature. This is a very, very popular database, and I'm just including this in here to show you where this comes from, because this is not something that I knew about years ago when I was a student. Some of you might know about it, some of you might not, but I just wanted to point this out here because this is a great resource for a lot of you that might be doing signal or image processing stuff. But okay, images are matrices. We could do matrix operations on them, including matrix decompositions, and of course, we're going to want to do our SVD, everybody's favorite SVD. And you'll see here, this is the image of our U matrix when we decompose our boat with SVD. This is our sigma matrix, and it looks like it's empty. We'll explain why that's the case in a moment. And we also have our V transpose matrix. Now, what I hope you'll notice with the U and V transpose matrices is that near the left-hand side of the U matrix, we see a lot more aggressive distortions. With our V transpose matrix, we see much more aggressive distortions near the top of that matrix. But what exactly is going on with our sigma matrix? Why does it look empty? Well, if you recall, our sigma matrix is a square diagonal matrix with our singular values running from greatest to least down our diagonal. All of them are strictly positive. But this is what our sigma matrix is. And if we look at just the first 10 rows and the first 10 columns of our sigma matrix from the decomposition of our boat image, and we put that on a logarithmic scale, as you can see right here, you can see that the first few singular values are so much greater in magnitude compared to all the rest of them. By the time we reach the 10th singular value, it just looks black compared to the very, very bright white of our first singular value. And so that can honestly explain why our sigma matrix is so empty looking, because we have 512 singular values here, since our image is 512 by 512. And so now back to our full SVD, and more specifically, our U and V transpose matrices. The columns of our U matrix are our left singular vectors. The rows of our V transpose matrix are our right singular vectors. And when we matrix multiply them together, we will get a matrix. But more specifically, since these are singular vectors, this matrix will be a rank 1 matrix. And why is that particularly important or interesting? Because that rank 1 matrix is then being scaled by the scalar value of our singular value. And all matrices, and what the singular value decomposition is really doing, is it's breaking up our original matrix into combinations of rank 1 matrices scaled by the singular values. And those singular values, more importantly, are really just a numerical measure or a magnitude of how much each rank 1 matrix is contributing to constructing that original matrix, or in the case of this example here with images, how much that rank 1 matrix means to reconstructing the original image. Now to go back to our left and right singular vectors and our singular values, many of you that are familiar with eigenvalues might be familiar with them being referred to as eigenpairs, or at least the eigenvalues, with the eigenvectors being referred to as an eigenpair. This is what I like to call a singular trio, because we have our singular value and our left and our right singular vectors. And the magnitude of our singular value is strictly going to determine how much the rank 1 matrix that's produced through the multiplication of our left and right singular vectors has on reconstructing the original data set, or the original image, or the original matrix. So the general idea behind data compression or image compression with the SVD is that if you have some piece of data that is already in the form of a matrix and you can decompose it with SVD, what you could do is you could find a cutoff point, in this case what I'm denoting with the variable s here, and you basically cut off all the rest of the singular trios involved in this. And so in other words, what that's doing is it's not just chopping away singular values, but it's chopping off columns of our U matrix and rows of our V transpose matrix. And what that's going to mean is that in total, we're storing less total numbers when we decompose all of this with our SVD and chop things away. And so in theory, what will be left over with after we do that is an approximation of our original A matrix. All the dimensions will still work out when we perform the matrix multiplication, but when we matrix multiply all that together, we'll still get m by n dimensions back for an approximation of the original matrix. And what this is really doing is it's chopping away singular trios which have a singular value that is very, very small in magnitude, meaning it's going to have much less of an overall contribution in reconstructing the original matrix. And I think this can be best seen in this animation that I've produced. Again, the code for this is all at the GitHub, link in the description. I'm not going to show too much of the code in this video because I think that's something that most of you could look at and try to figure out on your own. On the left-hand side, we're going to be taking a look at our image as we introduce more and more singular values in producing that. But on the right-hand side here, you can see we have all of our singular values plotted out on a logarithmic scale. As we introduce more singular values in reconstructing the original boat image, it will be shaded with a bright red dot. You can see that our singular values range from being on an order of magnitude of 10 to the 5, all the way down to we have singular values in here that are less than 1. And so if we can chop away some of these singular values or some of these singular trios that don't have a significant contribution to the original image, we can compress that data. And so we'll kick this off here, and you can see that once we stop at 25 singular values, you can already pretty clearly see the boat. Now don't get me wrong, there's a lot of distortion, there's a lot of pixelation, it's not that clear of an image, but you can see that we're also using singular values that are all greater than 1,000. We have not used any singular values less than 1,000 yet, and already we can already begin to see our boat. If we continue this on even more, by the time we reach 100 singular values, you can see that we can very, very clearly make out all of our boats, the sky, the clouds, everything. Now, again, there are some distortions, there are some areas that are grainy, but nearly everything is there for our boat image. If we let this roll on even further, you can see that that distortion and some of that noise in our image does clear up quite a bit, but after we reach about 200 singular values, there's not too much that's changing with our image. We could just let this animation keep going until we reach all 512 singular values introduced, and you can see that at this point, there's not a whole heck of a lot that's changing between using different numbers of singular values, because the overall magnitude of our singular values are so much smaller than the ones used previously. And so for our boat image right here, which is 512 by 512 in dimension, it's going to take 262,144 integer values to make up this image. However, if we use our approximation with our cutoff point s, in this case in our SVD, and let's just say that we set s equal to the first 100 singular values, so we're only going to use the first 100 singular trios in producing this, and we keep everything in this format right here of where we have a singular value, left and right singular vector, and we're just combining all of them, we'll be storing 512 by 100 times 2 for our left and right singular vectors, plus 100 singular values, for a grand total of 102,500 integers to store an approximation of this boat image. If instead we want to store our singular values as a matrix, a 100 by 100 matrix for our sigma, will have 112,400 values. Meaning that even in both cases, we are storing significantly less total integers than we would otherwise if we wanted to just store the original raw image. Now, when we go and reassume our image and combine everything all together, it will be 512 and 512 in dimension. But if we leave it just in this format right here, that's going to be significantly less total integers that we are storing. And so that's where the data compression comes into play. Because we're chopping out all of the singular trios that have a negligible or very, very little impact in reconstructing the original matrix or the original data, or in this case, the original image. But what if we want to do this with a color image? Like, say, for example, this image here of the crab Nebula created by a bunch of fine folks using Hubble data. Many of you know that I research neutron stars, pulsars, magnetars, and supernova remnants, so I have to shoehorn in this stuff whenever I get the chance. And this is like one of the most popular images. What if we want to do the same thing with a color image? How would that work? Well, all these images are just groupings of matrices. There's a matrix for a red channel, a matrix for a green channel, and a matrix for a blue channel. And the way that that works is that they all get stacked up together to form the original image, and the value of each matrix will just tell each pixel how red, how green, or how blue it needs to be, and then when they get all merged together, they form the color image. This, very famously, is what we call a tensor. You can see that after we hit about 50 singular values, again, things are pretty pixelated, but everything is pretty much there. Certainly by the point that we are including more than 250 singular trios involved in this, we have most of the resolution of the crab image there already. And of course, you know, we can kind of see that, okay, it gets a little bit brighter as we start introducing or including more and more of these. And for a real world kind of like astronomy application, I would never try to compress this data with this method. But again, in theory, it would mean we're storing less total numbers to represent this data of this image. And with that animation, I used the same cutoff point for each one of the different channels. But there's no rule that says you have to use the same cutoff point for each of the different channels. If you have an image that is much more of a red component than a blue component, you can set different cutoff points for each one of those. Now, don't get me wrong, that's going to change probably the overall look of the image ever so slightly, but that's in theory something that you could do. And so imagine for a moment that our boat image right here has color components to this. Let's just say, for the sake of argument, it's 250,000 integer values that it's going to take for each one of the channels of the image. I think this is 1024 by 1024 in dimensions, but I'm not sure. But for the sake of argument, let's just say that it's 250,000 pixels for each one of the different channels involved. That means it's going to be 750,000 integers that we're going to need to store to produce this image. And if it's on a similar scale to what happened with our boat, where if we use the first 100 singular values, it's going to be roughly about 100,000 integers that we have to store. You're talking about storing 750,000 integers versus 300,000. And so hopefully you can see just how powerful and interesting this is, and that we actually can compress data using SVD and linear algebra. Now, in most real-world applications, this is not the most useful, but this does have some quite large implications. Most importantly, that singular values are a good measure of significant components of a matrix, or in this case, of an image. And that's something that we can talk about in greater detail next time. For now, I just want to thank you all very much for watching. Hopefully you found this interesting, informative, helpful. So this is definitely one of the more interesting or cool applications of linear algebra, and so that's why I wanted to share it. It's definitely one of the more interesting or impactful applications of singular values in the SVD. But I want to thank you all very much for watching, and I hope to see you all again next time.